Hi, I'm Nick, and this is our engineering video for our senior project, an electromagnetic actuator for Camless engines. Starting with the problem statement, we are to design an electromagnetic actuator that could be implemented on a modern engine. This included the research, manufacturing, and testing involved. After defining the problem, we broke the project up into three main components: the actuator itself, the control system, and the test stand. To efficiently complete this project, we followed the engineering design process. This started with researching engine function, valve timing, and electromagnetism. We then conceptualized solutions and evaluated them using programs such as FEMM, MATLAB, and Excel. Finally, we made a detailed design, which then allowed us to move forward to manufacturing and testing.
Hi, I'm Charlie and I worked on the analysis and design of our electromagnetic actuator. For the materials of our actuator, cast iron was chosen for the core for its high magnetic saturation limit, steel was chosen for the case due to its low cost and ease of machining, and copper was selected for the coil for its high conductance. With the general shape in mind, we performed extensive analysis to find the ideal dimensions of our application. Most of the analysis was done in an FEA program called FEMM. This program is used to analyze all sorts of magnetic machinery. In our case, we used it to find the force produced by our actuator. FEMM is compatible with MATLAB, so I was able to write an optimization program to find the dimensions of an actuator that maximize actuation speed for a given valve spring stiffness. This program accounts for all the moving parts of the valve train and actuator system and uses an evolutionary method to find values such as the diameter and thickness of the actuator core, the dimensions of the case that encloses the actuator, and all the parameters of the coil. After letting the optimization program run for 2 weeks, the fastest opening time was found to be 14 milliseconds. After careful analysis of the program's results, we discovered that the relationship between the force produced and the weight of the core was such that speeds higher than 14 milliseconds cannot be achieved. This physical limitation stems from the saturation limit of the iron core. To achieve higher forces, the core must be larger, which results in a larger moving mass, which in turn requires more force, and so on. I'll pass it off to Daria now to talk about our control system.
We created a data acquisition system in order to validate our design that utilizes an accelerometer. A program first runs on our PC. The program prompts the user for a file name, as well as number of cycles for the actuator and the frequency. The actuator runs and the accelerometer reads data. It outputs the data to the user, as well as writes the data to a CSV file. This data can then be used for further analysis.
Okay, so what did we learn? Well, the 14 millisecond minimum opening time that we were able to achieve was not sufficient for our needs. Engines generally, at the RPM ranges they operate at, the valve opening times need to be between 3 and 6 milliseconds. And this was mostly due to the physical limitations of our solenoid design, where to get both the force and the speeds that we needed, the solenoid would have to be much, much larger than we would be able to reasonably fit inside a car or mount on an engine. And to get around this, future versions would have to use a different approach. They could potentially use a voice coil actuator, which replaces the iron core of a solenoid with a permanent magnet, which increases the strength of the magnetic field and gets you more force. Potentially also, either that could be used in conjunction with some mechanical energy storage system like springs, or you could use hydraulics and pneumatics to provide the force while you still use solenoids to do the timing. Now that said, we do have some things that we developed that can still be used, like the test stand, and our testing procedure is something that can carry on into further designs. So it was, was not entirely in vain, thankfully. So with the research that we've done, hopefully people can avoid the pitfalls that we've found and move forward with our research and development as a base. Thank you for watching.